Hello everyone. Now we have to discuss the analysis of unbalanced system. So last class we had a discussion that analysis of balanced system. Now we have to discuss the analysis of unbalanced three-phase system. So why it is unbalanced? Because when the loads in all the three-phase systems either in star connection or in delta connection are not identical to each other, means what? They are not balanced, means the magnitudes of currents or voltages are not equal. Obviously we can say that the system is unbalanced system. Okay, we have to write that point. When the loads in all the three phases are not identical to each other, right? Either it is star or delta connection. In all aspects, that's it. Okay, when the loads in the three-phase system are not identical to each other, either it is star or delta connection in all aspects, then the system is said to be unbalanced system, right? That is, what are the reasons to get the unbalanced in the system? So reasons to get unbalanced. Reasons. First one is unbalance in winding of a three-phase equipment like three-phase induction motor. Unbalance in winding of a three-phase equipment like three-phase induction motor. Supply system is three-phase alternator, like that the load system is what? Three-phase induction motor. So induction motors are nothing but three-phase loads. Okay, next one, unequal load on the system. These are the main reasons to get the unbalanced system, right? Then the phase currents in delta and the phase or line currents in star connection differ due to what? Due to unbalancing, right? So the phase currents in delta and the line currents as well as the phase currents in star differ in unbalanced loading, giving rise to what? A neutral current. We all know that in balanced three-phase system, the summation of all phase current should be equals to 0, all line current should be equals to 0. But in that case, we don't have any neutral current because all are balanced, right? We don't have any neutral current. But in this case, all three phases are unbalanced. Obviously, we are going to get the neutral current. If we add the individual currents, for example, consider phase currents, obviously by adding those three phase currents, we will get some neutral current due to what? Unbalanced load, right? You can write that point. The phase current in delta or phase, or you can write and phase or line current in star. Connection differ in unbalanced loading, right? Clear? Which giving rise to what? Flow of neutral current. So obviously we have a neutral connection in star, we don't have any neutral point in delta. So in case of star connection, IR plus IY plus IB should be equals to IN, right? Obviously in star connection, IR plus IB plus IB, which is equals to IN. There is a neutral current. There is a neutral current. Right? So in this context, we may clear that when the supply neutral and the star point is interconnected, the supply neutral and star point in load. So this is supply system, this is load system. So when the supply neutral as well as the star point in load are interconnected, obviously we have a separate wire that is neutral to return back to the source. Obviously we need a current, we need a wire, sorry. So that is to carry IN. So that fourth wire is needed to carry neutral current from load to source. Okay, in this context we may clear that when the supply neutral and star point in load are interconnected, it is called, what is the system? 3-phase 4-wire system, right? 3-phase 4-wire system. This is very important. For example, in the exam, 3-phase 4-wire system has a line current of 20 amperes. Means what? Star connection system. Okay, like that. While for delta we don't have any neutral point. While for delta there is no neutral point available. Therefore that system is called as 3-phase 3-wire system only. Okay, now we have clear idea why it is called as 3-phase 4-wire system, why it is called as 3-phase 3-wire system for delta. 3-phase 3-wire system. This is very important point. Okay, next, due to flow of this unequal currents in each of the phases, a voltage appears at the neutral and its value can be VON. In case of balanced system, we don't have any neutral current, obviously we don't have any voltage, neutral voltage, but due to this unequal currents, obviously we are having a neutral voltage. Okay, before that, first we have to draw the connection diagram, how we can get the neutral current and how we can get that fourth wire in case of star connection. Okay, let us say this is supply system, like that. Let us take okay, so this is what R, this is Y, this is B, like that we have R, Y and B. See, from supply to load we have a connection, like that. Y phase, like that. B. Okay, from supply to, clear? This is the supply system. Three phase supply system. This is three phase load system. Okay, three phase supply system, three phase load system. Clear? Then the current through this line is what? Obviously it is IR. The current through this line is what? Obviously it is IY. The current through this line is nothing but from source to load. Clear? Then this is the neutral point in supply system, this is the star point in load system, right? So due to unequal currents in the system, obviously there is a neutral current, because IR plus IY plus IB, which is equals to IN. Therefore because of that neutral current, obviously there is a voltage between this supply neutral point to load star point. Then this is first wire, this is second wire, now this is third wire, now we have fourth wire. This is the fourth wire, right? This is what? A neutral connection, neutral wire. That's why the star connected system is called as three phase four wire system, and the voltage across this point is what? We can call it as VON. Due to what? IN, due to neutral current, right? I think it's clear now, right? Now we have to write one point. Due to flow of unequal currents in each of the phases, a voltage appears. Okay, at neutral, and its value can be determined as follows. So because of this neutral current, because of this unbalanced loading, we have a neutral current. Because of that current, we have a neutral voltage, that is VON. Now we have to derive that value of VON. Okay, let us consider the current in the load is nothing but IR, IY, IB, right? the currents in each line being IR, IY and IB, right? See, this is a star point. This is star point. So it's star point O at star point O by KCL. We all know that IR plus IY plus IB, which is equal to 0. This is we want, right? So based upon this statement, we have to get that neutral voltage. Means there is a voltage between neutral point of a supply system and star point of a load system. Okay. So from this IR is what? We all know that I is equals to simply Vy, right? I is equals to Vy. Therefore, we can write now. Okay, IR which is equals to what? VR into YR. Sorry, here the load is what? Let us consider admittance. Okay, you can consider impedance or admittance, but here I am considering admittance. Okay, I is equals to V into Y, right? IY is equals to what? Vy YY. IB is equals to what? VB YB. So based upon this statement, IR plus IY plus IB is equals to 0. Therefore, sorry, the current through that branch is nothing but VRO. Sorry, VYO, VBO. Okay. Then we have what? VRO YR plus VYO YY plus, or you can say not, VB not YB, which is equals to 0, right? From this VRO or VR not, VY not, VB not, we have to get. To get VR not, see, from here to here VR not, right? From here to here VRN. So apply KVL, we will get VR not, from here to here VON, here to here VRN, right? So to get VR not, we have what is that KVL? VN not, VNO. Okay, right. To get VR not, we have VRN minus VON. To get VR naught, we have what? VRN minus VON into YR plus, like that, this is what? VYN minus VON into YY plus, like that, this is what? VBN minus VBN minus VON into YB, which is equals to 0. So from this we have VRN YR plus VYN YY plus VBN YB minus, we have what? VON YR plus YY plus YB, which is equals to 0. So from this we can get the value of VON, which is equals to what? Which is equals to what? VRN YR plus VYN YY plus VBN YB by YR plus YY plus YB. This is the value of voltage due to unequal loading. Okay. If we have impedances, for example, if load is in terms of impedance, if load is in terms of impedance. Just we know that y is equals to what? 1 by z. That is, just you have to replace the y with 1 by z, right? Then you will get the equation as what? Vrn zy zb plus vyn zr zb plus vbn zr zy by zy zb plus, this is with respect to impedances. Okay, this is the neutral voltage due to unequal or unbalanced load in the system. Okay, this is the voltage of that. Next we have to write where VON represents the neutral shift. What is that neutral shift, sir? Means unequal loading. Means let us take for example, this is R. Okay, let us take Y like this. Unequal means what? Imbalance, right? This is what? B. C. The magnitudes of R phase, Y and B phase are unequal, like that there is no phase angle between each of the phases. There is no proper phase sequence, right? That is, there is no phase displacement between any two phases. That is 120 degrees phase displacement. Between R and Y we have what? 90. Like that between Y and B we have 120. Between R and B we have 120. So like this we have to represent in unbalanced three-phase system. Okay, let us say because of this unbalance we have a neutral point. This is load. Okay, we have a neutral, for example, okay, at this stage. Okay, this is N. Okay, then because of this R phase, because of this Y phase, because of this B, then where is neutral shift? Because of that, this is the neutral shift. Clear? This is the perfect representation of this analysis. So there is a neutral voltage due to neutral current in the system due to the system. Where is the neutral shift? We can provide. This is what? Neutral shift. This is the perfect analysis of unbalanced loading. Okay, that's it. Now we have to discuss properties of unbalanced loading. Properties of unbalanced loading. First one is what? Waveforms are disturbed in terms of magnitude and phase angle. Waveforms are disturbed in terms of magnitude and phase angle. Just now we have discussed that point, right? Second point, current flowing through phases. Current flowing through phases is not same. Third one, neutral connection is needed. Fourth one, power loss is more. That's it. These are the very important properties of unbalanced loading. Okay. See, why we are getting this unbalanced loading? Due to what? Unbalance in winding of a three-phase equipment like three-phase induction motor and unequal load on the system. Means what? The phase currents or line currents or phase voltages or line voltages are not identical to each other in any manner, whether it is magnitude or whether it is phase sequence or magnitude, both are unequal. Okay, that's why we are going to get unbalance in the system. So because of this, there is a neutral current. If we consider a star connection, obviously the system is called as three-phase four-wire system, but we don't have any neutral point in delta connected system. That's why the delta connected system is always called as three-phase three-wire system. Okay, and because of this, there is a neutral voltage, and this is the derivation for that neutral, and this is the representation of what? Neutral shift. That's it.